Okay. That was organic chemistry. So we were on this topic. I was telling you about the carbocations, yeah, which was the topic? Properties of halogenoalkanes. So this was our class on 22nd February. Okay. Let me just open the book, right? Just a minute, Peter. AQA. Halogenoalkane, which is on page 206. Okay. Okay. All right. So halogenoalkane, and we need to do the reaction that is reinforcement. Have you revised it, Zena?
Yeah.
I told you. All right. So, okay, fine. So we were on halogenoalkane, and did I explain you the polarity and other stuff? All right. So now we are going to do the main reactions of the halogenoalkanes, right? So the first reaction we are going to do is combustion reaction. No, I do need to do the properties first. All right. There it is. So, properties of halogenoalkanes. It is also called as haloalkane, right? Now, the physical properties are number one, they form the homologous series, physical and chemical properties, and chemical properties. The they form the homologous series with general formula. Have we done this, Sena? But I'm so sorry. Actually, I take so many classes that I forget that at which point did I leave the student. So if you can kindly help me in identifying that which topic we were doing last time when we had the class.
We've done this.
You have done this? All right, fine. So we also did the volatility as well?
Yeah.
No? All right, fine. So if volatility, bond polarity is also done? CX bond polarity.
Yeah.
All right, so we are done with this. So we'll simply start we will simply start the substitution reaction then. That's why I always write what we do. Anyway, all right, a nucleophilic
We've done that
substitution.
as well.
We have done this as well. That's great, by the way. Oh, so if we have done this, then what is left? We have done with sodium hydroxide, and we have done the mechanism as well. Yeah?
Yeah. Yeah.
Oh, we did the mechanism. Wow, great. So now then elimination reaction. I think we haven't done the elimination reaction. Yes?
Um,
Should I
I think
check?
we have. Um,
We have. Let me check because this is number of carbon chain, the strongest. Easy. Halogenoalkane. No, better look. We have done halogenoalkane. We did this. It's all about the properties. Then we did this whole thingy that is about the down the group, atomic radius increases, bond length increases, and then order of the strength of the CX bond, then which is a good electrophilic center, then all these points, then nomenclature, then polarity, then number of carbon atom in the chain, then the nomenclature, then carbocations, primary, secondary, and tertiary carbocations. That's about it. Oh, yeah. So this is, yes, the formation of carbocation. Now, I haven't completed this. Look, I have done this, that carbocation is formed, and this carbocation, now I didn't do the next reaction with it. Look, yeah. No, I didn't do this reaction. So I will complete it, and then I will go to the elimination reaction. Does it make sense?
Yeah.
All right. So I'm going to take from here. uh, from this point, I will continue, right? So I'll do like this. A carbocation is formed between, this is the carbocation, and you know that this is called as tertiary carbocation. So now in the next step, the leaving nucleophile will again attack on this electrophilic carbon atom, and you need to draw the arrows from the lone pair to the electrophilic carbon atom. Never start the tail of the arrow from the negative charge, otherwise you will not be getting any credit. So now it becomes CH3C, CH3, CH3, and Br. So now this is called as halogenoalkane. All right. So we did this. I hope it's clear. Now, the reaction is with sodium hydroxide. Before starting it, I'm going to take it down. And before starting this, we were doing the uh, uh, substitution reaction. So substitution reaction is done. Let's suppose CH3, CH3, and CH3, and then comes halogenoalkane, that is Br. Now, when it reacts with sodium hydroxide, which is aqueous, this is very important. Let me highlight it. This aqueous thing is really very important. Now, what is going to happen? Better, yeah, there are few reactions which are left. Nucleophilic substitution reaction. So what is going to happen, that this bond will get polar, partial, because bromine is electronegative in nature, so it is going to get a partial negative charge, giving a partial positive charge to the carbon atom. Now, I will do like this. Instead of mentioning sodium hydroxide, I will simply mention nucleophile. So it will react with Nu, having a negative charge, but it is going to do like this. For example, first of all, this bond would be broken, and this is the mechanism. So I'm going to get CH3, CCH3, CH3 plus plus Br negative. By the way, I am not going to make the nucleophile in the reactant, rather I will make the nucleophile on the line. Now, why I am doing this? I am doing this beta because it is again heat under reflux. Heat under reflux. This is very important, Zena. Why I have shifted it from the reactant to this side? The reason being, nucleophile simply shows its presence. It does not it does not involve in the reaction, right? So what happens actually, just by looking at this nucleophile, just because of the presence of this nucleophile, this tertiary halogenoalkane, by the way, this is tertiary halogenoalkane. So this bond between this CX bond, which is between CBr, it gets broken because bromine is electronegative in nature. So it gets broken. And then what is going to happen? We are going to get sorry, we are going to get tertiary carbocation plus Br negative. Now, in the next step, we will see the involvement of in the next step, we are going to see the involvement of the nucleophile. I am keeping it generic. So this is the second step. CH3, CH3, CH3. This is the tertiary carbocation. Now it is going to react with sodium hydroxide, which I wrote in the form of nucleophile here. So in order to make it generic, I will not write sodium hydroxide. I will simply write nucleophile. And then what is going to happen? This lone pair will attack on this carbocation because it is deficient of electron, having the proper positive charge, and we are going to get This product. Now this is a compound. Now you can write down the overall reaction. This is the mechanism of the reaction. If you are going to add it up, beta, what happens that this will get cancelled with this, and what is left, this thing plus this, and it will form this and this. Are you getting my point, right? However, in order to make it more generic, I am going to rub this as well, and I will write X here, so it will be very clear that X would be given out as a leaving nucleophile. Now, when you are going to add it up better, you will get CH3, CH3, CH3X plus Nu negative, and you are going to get CH3, 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 and Nu plus X negative. Now, if you want to show the curly arrows on the overall reaction, so you will do partial negative, partial positive like this, and then you will show an arrow, a curly arrow, which is going to attack on the electrophilic carbon atom to give the product. This is the generic equation. If you are going to change this Nu, let's suppose with NaOH, and this X with Cl, and this X with Cl, so what is going to happen? Let me write. I'm going to rub it afterwards. So if I write NaOH instead of nucleophile, and I'll replace this X with chlorine, what is going to happen? We are going to get sodium chloride, and this OH will be substituted here, and we are going to get an alcohol. Does it make sense?
Yeah,
Yes, Zena. Zena, if there is a problem, do tell me, bete. I will explain again.
it makes sense.
Good. Now I'm going to change it. So this was the overall reaction. This is called as nucleophilic substitution reaction. Why, Bete? Because one nucleophile, here it is, one nucleophile, this is called as the leaving nucleophile. Let me write it down so that when you repeat it, it is very clear to you. This is leaving nucleophile, and this is attacking nucleophile. And the name of the product depends upon the type of the nucleophile or the kind of the nucleophile. Name of the product. Now I'm going to write it in front of you, and you will immediately get it. Why it is called as nucleophilic substitution? Because one nucleophile, I said that X is the leaving nucleophile. So that means this nucleophile is going to take the place of this nucleophile, which is going to leave. So as one nucleophile substitutes the existing nucleophile, this is called as nucleophilic substitution reaction. Now, Bete, what I'm going to do, I am going to change it. As in your book, the common examples given was hydroxide, ammonia, and cyanide. So that means that these examples are in your syllabus. So I'm going to do it right now. So I will simply, I have started doing it for the tertiary halogenoalkane. You can, it is not a hard and fast rule, but you can do it for the primary halogenoalkane. So if I will take primary halogenoalkane, this would be the primary halogenoalkane. The only difference is in the number of alkyl group. You know that the carbon which is attached to the halogen atom, if this carbon in turn is attached to three R groups, that is called as tertiary halogenoalkane. If this carbon which is attached to the X, if this carbon attaches to only one R group, that is a primary halogenoalkane. I hope it makes sense because last time we did this, right? So, Bete, now it is going to the mechanism. I am doing the mechanism, Bete. Yes, Zena, are you following me, Beta?
Yes.
What happened? Any confusion, Bete?
No.
All right. So if I am going to react it with sodium hydroxide aqueous, what is going to happen? This bond will be polarized and it will get broken. And I am only taking hydroxide, I'm rubbing this sodium, and I'll keep it in the form of a nucleophile. Now, this lone pair will attack on this electrophilic carbon atom, and we are going to get X H, and then what we are going to do, we are going to write OH here plus Br negative. And what we have formed an alcohol. So halogenoalkane can be easily converted to into alcohol by using sodium hydroxide. Now, if you are confused that why didn't I write sodium hydroxide, it doesn't matter. I can show it like this, NaOH, and then I am going to get NaBr, and this negative charge will be removed. So it's one and the same thing. I hope it clearly makes sense to you. All right. Now
Okay.
let's do the mechanism. This is the overall reaction. Overall reaction. Now the mechanism would be CHHBr negative Br, and in the first step sodium hydroxide will be shown on the arrow because this is not participating in the reaction, it is simply showing its presence. So this would be heat under reflux, and this bond will get polar and this will break down, and I am going to get CH3CHH plus sign plus Br negative. This is the first step. Now in the second step, what is going to happen, that number 2 step, I will take this species. So CH3CHH positive plus Br OH, sorry, OH, this OH or sodium, whatever the case may be, will be taken, and it is going to attack on this, and we are going to get C, H, H, and OH. So this is the formation of alcohol, primary alcohol. If we are going to take primary halogenoalkane, we are going to get primary alcohol. If we are going to take secondary halogenoalkane, secondary alcohol, and if tertiary, tertiary alcohol. This is the first nucleophilic substitution reaction. Now, this is the end. I'm repeating again and again. This is the mechanism. Let me write mechanism here. Mechanism of the above reaction. Now, the second one, elimination reaction. Sorry, no, not elimination. I should better rub it. Now, the next reaction is with cyanidine. So, the second reaction would be halogenoalkane. We haven't done this, Zena, right? Cyanide ion.
No.
All right. So again, Bitte, I'm going to take halogenoalkane, CH3CH, H, and again this time. Now, do you want me to do it in a generic form or should I write cyanide? Tell me, please, what to do.
You can write cyanide ion.
Okay, fine. So I'm putting X here, right? You can take it as chlorine, bromine, iodine, whatever the case may be. Now I'm doing the mechanism, right? So when I'm going to do the mechanism, all right, first of all, the overall reaction, I'll write overall reaction here. So according to the overall reaction, it is going to react with cyanidine. I'll put a lone pair here, negative charge here, and then this would be partial positive, partial negative. This bond would get broken, and the tail will start from this lone pair, and I am going to get CH3CHH, and now I'm going to get cyanide plus X negative, which is the leaving nucleophile. This is the overall reaction. Again, as I told you earlier, that this should be alcoholic. All right, alcoholic and heat under reflux. These are the conditions. As I told you earlier, whenever you write any reaction, number 1, write reactants. Number 2, write products. Number 3, write reagents. Number 4, write conditions. Number 5, if present. This is not 100% that every time you need to write observation. Number 5, observation. Number 6, equation, and number 7, mechanism if required. So these are the 7 things which you need to mention for the overall reaction. So for example, in this case, Pite, reactant, these two are the reactants. Products, these two are the products. Reagent, this can be come under reagent, but this actually alcoholic thing, definitely it comes in the reagent, because it makes a difference whether you are taking aqueous or alcoholic. Now the next step is condition. Condition would be heat under reflux. If present observation, there is no observation. And then equation, this is the equation. And then the mechanism, I am going to show you the mechanism. So can you guide me in writing the mechanism, Zena?
Um, would it be CH bonded to CH3 H and H bonded to X?
Well done.
And
Then,
X is delta negative, carbon is delta positive,
okay, yes. This would be broken. What should I write next?
plus CN.
No, beta, not plus. I will make an arrow, and on the arrow, I will write Cn negative. Okay, that's what I'm telling you in the mechanism. Okay, and now bitte, this, if this Cn is not written, that's what I'm telling you. If this Cn is not written as a reactant, that means that, and if it is written on the arrow, that means it is not taking part in the reaction. If it is written here, that means it is taking part in the reaction. So in the mechanism, in the first step, it is not taking part in the reaction, and we are getting CH3, CH plus, that is carbocation, plus X negative. Now see, there is no involvement of cyanide ion in the first step. However, as soon as I am going to write the second step, I am going to copy this down. What is this called? This is called as carbocation. We have already discussed it in detail. So I will take the carbocation again, plus, plus, now I will show cyanide ion here, bitte. When I show cyanide ion here with a sign plus, that means then towards the reactant side, that means that now it is taking part in the reaction, and you will draw the arrow from here onto the carbocation, and bitte, we are going to get CH3, CHH, and cyanide, CN. I hope it's clear, right? And now what have you formed? The product is called as what? This is halogenocyanide, right? So it's entirely up to you that you do it in this way in order to, or you can call it nitrile. So right now, how many carbon atoms are there? Only 2 carbon atoms. So the product is called as ethano nitrile. This is the name of the product, right? In your book, it is written that the product is called as nitrile, but I have written the whole name, that because there are 2 carbons, so this is called as ethanonitrile. But this is clear. This is the second reaction. The first reaction was a reaction of halogenoalkane with sodium hydroxide. I'll write here. Reaction of halogenoalkane with sodium hydroxide equals 1. This is 1. So this is now 2, 2, and now I will write 3. Any questions, Zena?
No.
All understood?
Yeah.
All right. Now the third reaction. Reaction of halogenoalkane with ammonia. Ammonia. All right. Now, bitte, always keep this thing in mind that ammonia should be written like this: NH, NH2. Instead of writing like NH3, write it HNH2. So this is a proper representation. It will help you a lot in forming the product. All right. So, however, in your book, it is given in a different way. So I'm going to follow that. They are not using this, which is quite surprising. But anyway, I will not use this. But eventually let me write it so that eventually you will see that you are going to get the same thing I am talking about. So there is no difference between the two. Can you see this? This is also ammonia, and this is also ammonia. but I have written it in this way so that it can be easily done. I'm not rubbing it. This would be the functional group which will be used, that is called as amine. So I'll show you how we are going to do this. All right. So actually, this H will combine with the Br or Cl, whatever. Like if I make the halogenoalkane like this, HCH CH3, and let's suppose if I write Br here. So you know what? Let me highlight the HBr would be formed, and NH2, and NH2 will take its place here. So this would be amine. Are you getting my point, Zena?
Yeah.
All right, so this would be the overall reaction, but in your book they have given it in a different way. So, but I'm going to follow that. The reaction of halogenoalkane with an excess concentrated solution of ammonia. Now, what is the reagent and condition? Excess, number one, and number two, concentrated solution of ammonia, right, in ethanol. And again, the reagent is, you need to have the medium. You need to prepare it in a medium. Most of the time it is water, which is called as aqueous, but sometimes we take alcoholic. So I will take alcohol. Right, now let's do the reaction the way it is given in your book, but you are going to get this product NH2 in the product. Now look, it is done under a sealed container, sealed container, under pressure, under pressure. And that's a closed vessel or sealed container, whatever the case may be. So have a look, bitte. HCX. Now, when it is going to react with N, H. Now have a look. Partial positive, partial negative, partial positive, and partial negative. And this has the what? This is going to have the lone pair. Now again, the same thing, beta, that it will get partial negative, partial positive, the bond would get broken, and this is going to take its place. So what we are going to get, beta, we are going to get copying the previous reactant like this, RH, and now this is going to be formed, which is called as an intermediate. This whole thing will join here. So have a look. This would be NH, H and H, and plus X negative. This X, I'm talking about this X negative. Now, what is going to happen? You know that the valency of nitrogen is 3. Right now, the valency of nitrogen is 1, 2, 3, 4. So, what happens? That means it is a highly unstable compound. So, this nitrogen is not going to keep a valency of 4, because this gives it a positive charge. So, nitrogen doesn't want to have this charge. Right now, you should write it, although it's not given in your book, but you should write a positive charge here. Now, what is going to happen? This positive charge, this positive hydrogen, that means it is going to break its bond to this side. And what is going to happen? That we are going to get HC, R, H, then N, then H, and then H. Now this is given out as H positive. So what is left, beta? NH2 is left. That's what I was telling you continuously, that no matter what you do, you are going to get NH2. All right, NH2 plus X negative. However, your book has done another reaction, that is, they have taken another molecule of ammonia, and this hydrogen, which is given out as a proton, it will be accepted by the lone pair of nitrogen to make a dative bond, and we are going to get NH4 positive. Alongside this, we are going to get NH4 positive. Does it make sense?
Yeah.
Yeah. However, again, this is your product. This is your product. Okay. Now, this is done. We have done 3 reactions. So, how many reactions we have done? We have done 3 reactions. Halogenoalkane number one. It it is. RCH2 and H2. This is primary amine. Then RCH2OH, alcohol. You can make, these are the, what you can make. From halogenoalkane, you can make amine, you can make alcohol, or you can make, that is RCH2C triple bond, and that is nitrile. So these three classes can be made from alcohol. All right. So by the way, you can not only do it with the primary amine, you can also do it with secondary amine. And as I told you earlier, you need to increase for secondary amine, you need to increase the R groups. So if you want to write secondary amine, that would be RCH2 2NH. So this would be secondary amine, right? So then now the next thing would be or it can be simplified. Why to make it difficult? That would be R2CHNH, like this, like this. So this is the secondary amine, RNH2, R2 and H. So you can do it like this as well, right? So this is the secondary amine which can be formed, right? So tertiary amine would be N, R dash, and R double dash. This could be tertiary amine. And same goes with the alcohol. You can take primary alcohol, secondary alcohol, or tertiary alcohol. You can form according to the thing you have taken. If you are going to take primary halogenoalkane, you are going to get primary alcohol. If you are going to take secondary halogenoalkane, you will get secondary alcohol. If you will take tertiary halogenoalkane, you will get tertiary alcohol. Does it make sense, beta?
Yeah.
All right. And nitrile is one and the same thing, that you will simply keep nitrile. Now, the other thing is that how to make other products from the nucleophilic substitution. Now, according to this, Pete, the alcohol you make, you can do the oxidation of alcohol if it is primary to get aldehyde, and then eventually it is going to change into carboxylic acid. This is after oxidation. I'm talking about alcohol now. I'm not talking about halogenoalkane. I'm talking about alcohol. Keep this thing in your mind. Now, as far as nitrile is concerned, if I will do acidic hydrolysis, that means if I'll break this bond from here, if I will add, let's suppose, OH, H, and HCl. If I will add everything now, I'm going to get RCH2, C double bond OH, plus I'm going to get ammonium ion. All right. So your book has not given the full reaction of this. They have simply mentioned that. This is called as acidic hydrolysis. I wonder why they have given it. Has your teacher taught you this?
Which part?
Yes?
Which part?
This part, this part.
Yeah.
So it means we need to do it in detail. All right. I think when alcohol would come, then we are going to do it, right? Otherwise, it will not make clear sense to you. So I'll keep this thing in your mind, in my mind, that I am in need of teaching you this. But right now, I will not teach you, because it is not concerned with halogenoalkane. We are actually concentrating on halogenoalkane right now. Okay. So as it comes along, I'll teach you. Now comes the elimination reactions. This is not, Zena, let me tell you, this is not connected to halogenoalkane. These are the reactions which are done afterwards. Got my point, Pita?
Yeah.
Elimination reactions of halogenoalkane. Now we will do this elimination reactions of halogenoalkane. Now, if you remember, I told you what is the meaning of elimination. Elimination means to eliminate something. What is the meaning of eliminate? To remove something. And what is removed? actually two small groups are removed. Two small groups are removed from two adjacent carbon atoms. Two adjacent carbon atoms, right? Now I will, and if you remember, I told you that you take sodium hydroxide. It can be taken in two ways, aqueous or alcoholic. If you are going to take aqueous sodium hydroxide with halogenoalkane, that means halogenoalkane plus sodium hydroxide. If you are going to use aqueous, you are going to get alcohol. So halogenoalkane will be converted into alcohol. If you are going to use alcoholic NaOH, you are going to get alkene. That means halogenoalkane will convert it into alkene. This is very, very important. This reaction is the hot favorite reaction of the examiner. Is it clear, beta? So let's do this now. First of all, again, as I told you earlier, that whenever you do the reaction, you need to keep these things in mind. Number one, reactant, product, reagent, condition, observation if present, equation, and mechanism. So we'll do like this. So first of all, are you getting this point that what happens when we are going to use aqueous and alcoholic? The reagent is the same, that is sodium hydroxide, but simply the solvent changes everything. Is it fine, Zena?
Yeah.
All right, so I am taking Bitte, I am taking 2 bromopropane. So, or simple bromopropane, because in your syllabus it is very simple. Otherwise, if I will take 2 bromopropane, then I'll see if it is given in the next. Let me check. Yeah, they have given, but they have started with the simple one. So I will also take the simple one. This is. mm, Zena, can you just give me a minute?
Okay.
All right. So this is HBr. Sorry for the disturbance. Now, the overall reaction, if I'm going to take uh, sodium hydroxide, let's suppose if I take sodium hydroxide or potassium hydroxide, keep this thing in mind, it's alcoholic. Now, overall reaction beta would be, I am going to get CH2 plus KBr plus H2O. This is the overall reaction, right? So that means that we are going to get this. Now, Betty, how are we going to get this? What is actually happening? Like, this is the overall reaction. Overall reaction. Now, actually, what happens? This group will be removed from two adjacent carbon atoms. So, what will be removed? HBr. HBr because it will be removed, and you know that HBr is a strong acid. So what is going to happen? It will form these ions. Now this Na, this I will do it with a color. This Na will combine with this Br to form NaBr or KBr. I will write here, and this OH will combine with this H to form water. Does it make sense? Yes,
Yeah.
I have tried my level best to make it as easy as possible. So this is the overall reaction, and we need to do the mechanism of the reaction, all right? So what we will do, the reactants are halogenoalkane. Number two, reactants are halogenoalkane and uh, sodium hydroxide slash potassium hydroxide. Okay, and then comes the other thing, that is condition. Condition would be boil the mixture under reflux. Number 3 is product. And alkene. Product and alkene will be formed. And then product, condition, and uh, boil it under equation. I have already written. Then mechanism we are going to do. Observation, it doesn't have any obsession. But by the way, this acts as a base here. This is very important. Now let's do the reaction. Um, uh, and all there is no water. Alcohol reagent condition. Reagent is missing. Reagent will be alcohol. Alcoholic solvent. That means no water present. All right. So now we will do the mechanism. Okay. The mechanism would be very careful about the mechanism because it's important. So the mechanism would be, I'll write C H H C H B R C H H and H. Now, in the first step, this would get partial negative, partial positive. The bond would get polar. This would be broken down. And then what is going to happen? The base, as you know, the base, it gives the electrons. So what is going to happen? It gives the electron to this side, to this hydrogen, which will break its bond with the carbon, and this hydrogen will be removed as H positive after giving the electron. As it is removed with H positive, that means it is leaving its electron here. So what we are going to get, beta, we are going to get C H H, and as it has, this one has already broken down, so I'm going to show it separately. Br negative. I'm going to show it separately, beta. This is broken down. And then what is the next thing? That is, as I told you, that this hydrogen is leaving its electron here and it is going out as only H positive. So what is going to happen? There would be a double bond here. This hydrogen will be copied. This hydrogen will be copied. And now plus this, as I told you, that this hydrogen is going out with a positive charge, so it will combine with this OH. Positive will get cancelled with negative, and we are going to get H2O. All right, is it clear? So is this mechanism clear?
Yeah.
All right. So actually what happens, the O, I'm talking about this OH ion. The OH ion uses its lone pair to form a bond with one of the hydrogen. One of the hydrogen. Which hydrogen, beta? This hydrogen. All right. So one of the hydrogen atom on the carbon next to CBr bond. Which Cr bond? So this on this hydrogen is on this carbon, which is next to the carbon, CBr bond. All right, beta. So now the next step, this is the first one. The number two would be number one. Number two would be the electron pair from the CH bond now becomes this electron pair, which has been given by this hydrogen, as this hydrogen is leaving without any electron. This electron pair is used up. I'm not writing because otherwise it will take a lot of time. This electron pair will be used to make a double bond. So I will simply write double bond to save the time. Now, the next one is the bromine takes the I'm talking about this bromine. The bromine takes the electron, these electrons, which are shared between carbon and bromine. The bromine takes the electron and leave as a bromide ion. All right. This reaction is very useful in making molecules with carbon-carbon double bond. Is it clear, Betty?
Yeah.
All right, so this is the end of this mechanism. Now, let's suppose that we have, now be very careful. If I take one chlorobutane, so have a look, 1, 2, 3, 4. If I'm saying should I go further along, Zena? Is it fine? If I know it's quite tough, but I hope that you are following.
It's fine.
All right, fine. So oh, I'll use different color. H. And as I told you, this is 1-chlorobutane. Now I'm trying to show you the influence of the solvent. So this is 1-chlorobutane. I have written it. I'm making two arrows down, one here, one here. On the first arrow, I am going to write I'll take sodium hydroxide here, but I'm going to write equus. So if I will write equus beta, this would be a substitution reaction. This would be a substitution reaction. And if I will again take sodium hydroxide, but this time if I am going to take alcoholic, then this would be elimination reaction. Elimination reaction. All right, so let me highlight this thing, this one, and this one. So now, if I'm going to take sodium substitution reaction, this will give rise to alcohol. And this will give rise to alkene. Now, Betty, what I'm going to get? Alcohol. What would be the name of the alcohol which I can make from 1-chlorobutane? Yes, Beta? Zena?
Yes.
What would be the name of the alcohol, Betty?
Oh, would it be 1-chlorobutane?
No,
Butanol?
but alcohol. Alcohol means that this chlorine will be replaced by OH. All right. So I am going to get 1, 2, 3, 4, and the OH now is replaced by Cl will be replaced by OH. This is. Are you getting my point? All right. So this is the change. This is the change. Here it is. But and this is substitution, repeating again and again that this is elimination and this is substitution. Now, if I'm going to use alcoholic sodium hydroxide or potassium hydroxide, I am going to get copying this down 1, 2, 3, 4 C's, but hydrogens would be. But now I'm going to get double bond and H and H. This is but 1-ene, right? So in this way, we are going to get the product. I hope it's clear. All right. Now that's it. And however, you can say that the other condition is this is equal, so it's cold sodium hydroxide bitter, and this would be hot sodium hydroxide, heat under reflux. All right, so this is the type of the alkane we are going to get. But now there is one more step in it, which is the most important thing, that what type of halogenoalkane will give the different product. For example, if I'll take, now in your book it is not written, but I'm writing it down. That is, what happens if we take unsymmetrical alkene? Now, be very careful, Bete. When I say unsymmetrical alkene, that means um, this one, 2 bromo. If you see that this is 1 chlorobutane, 1 chloro or bromo, whatever the case may be, butane. What happens if I shift this one to 2 chlorobutane? So let me make this. This will make a great difference. So this is now bete, this is CH3, H, 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 H. This would be bromine. Br, H. No, I'll use the same color. Oops, H, H, and H. So this is right now 2 bromobutane. Is it clear? Any confusion in this?
No.
No. Now see that what is going to happen. If now there are two choices. I'm doing alcoholic. Let me write NaO, or this time I will take KOH, alcoholic. Now we have two choices. The first choice is this, and the second choice is this. Are you getting my point? You can eliminate these two molecules from these two adjacent carbon atoms, or these two molecules from these two adjacent carbon atoms. Right, Zain? Are you following me, beta?
Yeah.
So if what is bothering you, beta, I'll explain again.
Nothing. I understand it.
All right, fine. So now I both the options. I'm taking both the options. First, this option. Now, if I will remove this, I'm going to get CH3, CH2, CH double bond CH2. All right, this is for pink one. I'm going to, this is, oh, just to color code it. Pink one, right? Now, if I will take the other one, that means blue one, I am going to get CH3, CH double bond, CH3. If I take the blue one, this is for blue one, where I use the blue highlighter. So what is this, Bitte? This is, are you getting it? How did I do that?
Yes.
So this is, Bitte, this is but. This is but 1-ene, and this is but 2-ene. Now, this would be, the surprising thing is, this would be a minor product and this would be a major product. Why is this so? This is because, bitte, the major product is, this is going to give isomeric alkenes. How come? If I will block this part, double bond, this would be C, double bond C, H, this H, and CH3 to this side. Now in the second one, H, H, and CH3 to this side. This is right now, this is the main chain. This is the main chain. So this is cis but 2-ene. And then if I flip this, this becomes CH3 will come here and H will come down, and this will remain as such, and this is called as trans, or like this, transbutene. Transbutene. So it's a very hot favorite question of the examiner, that when you are going to react 2-bromobutane with alcoholic KOH, how many products you will get. Most of the time students write but1-ene and but2-ene. They forget to make the isomeric alkenes, that is cis-but2-ene and trans-2-butene. So most of the time they forget the third isomer. So when you are going to do the reaction of 2-bromobutane, 2-bromobutane with KOH, you are going to get 3 products. Number one, um, butanene. Number two, cis-butene and trans-butene. So these are the three projects you are going to get. And by the way, if you check but1ene, you cannot make the isomers of this. How come? Let me draw this. This is the double bond. Let me uh, block it. So C double bond C. So these are two hydrogens, so H and H, and then one hydrogen to this side and this whole group to this side. So you know that this is the condition of cis-trans isomerism, that two same groups should not be attached to the same carbon atom. Otherwise, it will not give cis-trans isomerism or easy isomerism. In your book, it is written as easy. So cis-trans isomerism or easy isomerism. By the way, this trans is called as E. So let me write it here. E isomer, E isomer. And because this is called as cis Z. Cis is called as Z and E is called as trans. So this is about the halogenoalkane. The whole chapter is done apart from the last part, that is chlorofluorocarbons, that is with how ozone is being destroyed by the chlorofluorocarbons. So I have done the whole mechanism thing, starting the lesson, I think, from here. Is there any point which you want me to discuss again? So this is today's, I think, 1st March. I'm going to continue just making you clear that we have done this. Betty, anything you want to discuss?
No.
All is clear.
Yeah.
All right, that's wonderful, Zena. Now, the last topic, that how halogenoalkane affects the environment. So, effect on the environment. Actually, chlorofluoroalkanes, CFCs, chlorofluorocarbons or chlorofluoroalkanes. These are actually depleting the ozone layer, depleting the ozone layer, because you know that around the earth, 35 kilometers away from the earth, there is a blanket of ozone layer. So this is actually ozone layer, which is 35 kilometers away from the earth. Now, what happens, Vijay, when chlorofluorocarbons, they are actually destroying the ozone layer, and when they destroy the ozone layer, then what happens? That there would be some holes in the ozone layer, and what it is protecting us from ozone layer is protecting us from the infrared rays, or mainly ultraviolet rays. So it is protecting us from the ultraviolet rays. Actually, the chlorofluorocarbons, they are actually unreactive under normal condition. But when they go up, if they will be used a lot on the earth, what happens? Chlorofluorocarbons, they go up in the air, in the stratosphere, they react with the ozone, and then they change the ozone molecule. C C C C CFCs. This one, right? So if they go to the stratosphere and they react with ozone molecule, what do they do? Ozone molecule O3, they change it into O2. They change, for example, if it changes into O2, and then if I take, let's suppose, ClO2. All right, so it is going to react with ozone and it will change it into ClO3 plus O2. So that means that ozone is being changed to oxygen, and around the earth this oxygen is not needed. All right. So what is going to happen that the depletion of ozone will start occurring, and then there would be oxygen is not needed in the atmosphere that is 35 kilometers above the Earth. So what happens that there would be some holes in the ozone layer, and the ozone layer will be depleted. So we need to change them with something which is eco-friendly. So nowadays, actually, chlorofluorocarbons were used by the air conditioners and the freezers, but now they have changed the reactant or the reagent which was used in the refrigerators and ACs. So now they are using eco-friendly reagents, and they are not being released in the atmosphere in a huge quantity. And now the ozone layer is no more depleted. So we need to actually confine the use of the chlorofluorocarbons. Is it clear?
Yeah.
Any confusion, Betty?
No.
This is the end of this chapter. All right. This is the end of the halogenoalkane. This is quite a long chapter, and there are lots of mechanism in it, and they are important as well. Okay. So that's about it. Anything you want to discuss?
No.
So which chapter do you want to do the next one? The next chapter you want to do? This would
Uh,
be, yeah, you tell me.
yeah, we can do the next chapter.
And that would, we have already, just let me check. This is the alkanes. So we are done with, yeah, we have done alkanes. Yes. Yeah. So we have done alkanes. Then comes, mm, yeah, alkanes, and then halogenoalkanes, and the next one is alkenes. So let me write it. So the next time we will start it, the chapter would be written. That would be alkenes. We will start this. Okay. Now, Zena, it would be better. Have you done this chapter in your class?
Not yet.
Not yet. Okay, fine. But still give it a reading. I hope that you know about alkenes because we have already discussed it in detail. All right. So just go through it and then we will discuss it. Okay.
Okay.
All right. Any questions, Zena?
No.
All right. Okay. Thank you, Bitty, because I have my next class. So I have tried to give you the lost time. So now the lesson is complete. So it's okay. Right? Take care. Allah Hafiz.
Allah Hafiz.